Yes, please go ahead.
Okay, then once again, thanks, Dr. Janamejaya, for inviting me for this lecture. It's my pleasure to present it here. So maybe just to add a few points here to the introduction, my name is Ajay Pai, and I'm working at Infineon since the last 6 years here in Munich at the headquarters, focusing on automotive power modules. And we are looking into this new promising power module technology, which is based on silicon carbide, which we think has a lot of potential, especially for automotive applications. And this talk will be about these applications. So quickly, just to go to the agenda, I hope most participants here have a power electronics background. But
Yes, yes.
nevertheless, I think let's try to get our basics right first. I will give a short introduction to power semiconductors very quickly, and also to automotive applications, and why silicon carbide brings benefit, or why is it interesting for us.
Yeah, yeah. Take your time. It's fine. We'll
Yes.
very good on time. Take your time and go ahead.
Okay, thank you. And after that, I will get into the actual topic of the thesis. So the goal of the thesis was to find what are the benefits of silicon carbide modules as far as the efficiency of battery electric vehicles is concerned. And first, I will give a short glimpse into the background, motivation, goals, and so on. And then I will explain the power loss modeling approach that we have used in this thesis. And also a few points on experimental validation of the methods used, and then deep dive into the results of the investigation. And then, of course, after the conclusion, I will be available for question and answer sessions. Okay, so then let's maybe do a very quick short round of bridging into the presentation. So first of all, I think all of you here, I guess, have a power electronics background, and we all know that power semiconductors have a wide spectrum of applications. And most of us are familiar with, I'm sure, the typical mobile charging applications, which might cost something like $1 or $2, and which is one of, let's say, a very low power applications. But you might have also seen high power, high grid applications like the HVDC link that you see here, which connects the southern and the central grid of India. And this can transfer anywhere between 2000 to 2500 megawatt of power. So this is almost the size of a average power plant. And this could cost hundreds of millions of euros. So we know that power electronics has a wide range of applications. And a new and emerging, or a very promising application for power electronics or power semiconductors is e-mobility. I'm sure all of you have heard of Tesla, also Volkswagen ID, ID3, ID4. So the picture you see here is taken from a Volkswagen ID, which is based on the Volkswagen MEB platform. And if you look into it, the platform would look something like this. So this is a battery electric vehicle, meaning that there is no internal combustion engine whatsoever. So it's a battery. So the battery is normally in the center here, which you see in blue. And then we have an electrical machine here at the back, and the electronics on top of it. And then we also see a port where we charge the battery with an onboard charger. So now, of course, I mean, we have seen this, but if you look on the streets, I'm sure most of you will tell me that 90 or 95% of the cars you see on streets today are not battery electric vehicles. And but still, I want to stress that e-mobility is a very promising application for power semiconductors, and I would like to give you some figures for that. So first of all, the total semiconductor market today is roughly 400 billion US dollars. And out of that, automotive is roughly 10% market. Uh, and automotive power market is 10 billion out of that. So if you look at the total market share, this is maybe not such a big figure, but nevertheless, this has a huge potential to grow in the next years. Why? Because if you look today, a normal IC or a combustion engine based car has semiconductor content in the range of $100. But if you take a battery electric vehicle, this multiplies by a scale of 10, which means you will find around $1,000 worth of semiconductors in the battery electric vehicle. And I also have to stress that in a convention ICE based car, most of the semiconductors that you find are either microcontrollers or analog ICs, and maybe 20% of it is power semiconductor. But in a battery electric vehicle, most of the semiconductor content is power semiconductor content, which means out of the greater than $1,000 content that you see here, most of it is power semiconductors, which is why I think it's a very good field to be in today. It's a very happening field. And if you're still deciding which field to get into, then I could definitely recommend this field. Um and so of course, financial aspects on one side. There are also a lot of technical challenges which we have to solve in this field. And this is why we can be assured that there will still be more and more jobs to come in this field. So what are the technical challenges? All of you know that for power electronics, efficiency is one of the most important requirement. And for such a traction inverter application, we need in the range of 96% efficiency or more. And the higher efficiency is always welcome. Why? Because the range of an electric car is dependent highly on the firstly the battery size, and secondly also the efficiency of the components, which means if you have a higher efficiency, you can save on the battery size. And today batteries for electric vehicles are in the range of 100 to 150 dollar per kilowatt hour, which means if you can improve the efficiency of your inverter by 1%, you can save 1% on the battery. And this is already quite a large number. And as we will see later with silicon carbide, we can win roughly 4 to 5% or even higher efficiency, which means we can have the same cost saving on the battery. And this is a big number. And secondly, for automotive, failures are definitely not acceptable. Why? Because if there is a failure in the car due to a design defect, or due to the wrong choice of power semiconductor or whatever, then car companies will have to recall the car, and recalling a car is a very costly affair. So it can easily cost several millions, and some companies could even go bankrupt if they have to recall all their car models. I think we all know what happened with this company called Dakota, which manufactures airbags, and they had to recall a lot of their cars and were in deep financial trouble. So therefore, very low failure rates are acceptable for automotive applications. And for normal applications, we talk about parts per million. So how many parts per million could fail in the field? But for automotive, we talk about parts per billion. So this already should give a scale of how important reliability and quality is for automotive applications. And the third point is that, let's say we design a car. So this car has to run maybe in the heart of, let's say in South India, where the temperatures are quite high, maybe in Chennai, where it's 40 degrees Celsius. But it has to also run and be guaranteed to run in Himachal Pradesh, where the temperatures could be lower. Or for example, in Siberia, even where the temperatures could be much lower. And therefore, automotive systems have to be designed from -40 to even very high temperatures. So therefore, there is a wide range over which automotive devices should be able to function. And not only function, but also to be reliable and without failures. This is very important. And typical lifetime requirements are today 15 years or 300,000 kilometers, whichever is faster or earlier. And of course, people who have worked in the automotive domain will tell you that in a car, space is everything, weight is everything. Because when you bring down the weight of the car, you can win automatically in terms of range, performance, and so on. So therefore, these are the main technical challenges which we have to face in the field of automotive power semiconductors or power electronics. And if you look at a typical battery electric vehicle today, the topology would look something like this. This does not represent most of the cars, but I chose it here for explaining it to the audience. So we all know, I mean, in the end, the wheels have to be driven either by a combustion engine or in this case, with a motor. So the motor is here. This is an electric motor. And this motor has to be fed from a battery, high voltage battery, which is here. Today, it's typically in the range of 400 volt, but there are also 800 volt systems coming in. And we all know that battery is a DC device, or its output is DC, and the motor needs alternating current. And the job of converting or inverting from DC to AC is that of the traction inverter. And today, if you take a battery electric vehicle, traction inverter is the largest power electronic system. And also, like I said, quite a lot of um, um, cost involved also for the traction inverter. And then we also have systems like the onboard charger, which is used to charge the battery. And of course, HEV also has a small 12 volt battery, which we find in today's cars. And there has to be a power converter to connect the two voltage buses. And some cars also have a separate generator and inverter to feed back recuperation energy into the high voltage bus when we brake. There are also some cars, today it's quite common that premium cars have multiple such drive units. So the front drive and the rear drive, they're fed by two separate motors and traction inverters, which multiplies the number of power semiconductor components in the system. Okay, so then, so we have seen the application so far. So like I said, the heart of power electronics is the switch or the power semiconductor. And we all know that power semiconductors are not ideal. So what are the characteristics of an ideal device? It has to be able to switch off immediately and switch on immediately without any time delay or overlap between the current and the voltage waveforms. There has to be zero overlap between the current and voltage waveforms. But we all know this is not true. So none of the devices are ideal. So real power semiconductors are lossy. So what does this mean? So first of all, there is a finite time the switch takes to turn on or off. So if you look at the turn on waveform, we see that the current and the voltage, they take a finite time to go from 0 to 100% or the other way around. And this means there is an overlap or an area where both of them are non-zero. And this is what causes turn on losses. Similarly, there are turn off losses here. And during conduction, we also see that even though the device has relatively low resistance, there is still a small voltage drop across the device, which we see here with this dark or solid black line. And as long as there is positive current in the device or finite current in the device, so this voltage drop causes conduction losses. So therefore, there are switching losses and conduction losses mainly in the device. And there are also leakage current losses, which means that during blocking of the device, there is a small current still flowing in the device. But usually for high power applications, this is normally neglected, and we need not look into this in detail. So now the question is, how can we minimize the losses due to turn off, turn on, and conduction? So firstly, like I said, we should go for devices which can turn on and off faster, which means we have to reduce the time where we see the temporary rise and fall. So this has to be as quick as possible. And this means we have to use fast switching devices. And secondly, during conduction, the voltage drop should be as low as possible. This means we could go, for example, from a bipolar device like IGBT to MOSFETs. Why? I will come to this later. Let's ignore the leakage currents for the time being. Okay, so this is where silicon carbide can have a impact on the power losses. First of all, we all know that the performance of semiconductors are improving following Moore's law. And silicon has already been in the field for quite some time. This means that the improvement steps that we get from silicon are getting smaller from time to time. And this means we are close to the theoretical limit of silicon. So therefore, we have to look at other materials such as silicon carbide or GaN. So these are called wide bandgap materials because they have a bigger band gap compared to silicon. So band gap is the energy which is required to transfer electrons from the valence band to the conduction band. So higher the band gap, higher is the energy needed to do this. And normally materials with the higher band gap are more stable. So like I said, let's focus now only on silicon carbide because I think this is the most relevant material for automotive traction inverters today, apart from silicon, of course. So silicon carbide has a almost three times larger band gap compared to silicon. And this means silicon carbide is more stable. And breakdown voltage of a semiconductor is related to the square of the band gap. So this means silicon carbide has a 10 times higher breakdown voltage compared to silicon. And this means with the same thickness of device, we can achieve a 10 times higher breakdown voltage of the device for the same thickness compared to silicon. Or for the same breakdown voltage, silicon carbide can be 10 times thinner compared to silicon. So this means there is a huge potential to bring down the forward resistance, which is dependent on the thickness of the drift layer. And this means we can reach lower conduction losses. And the second thing is, today, if you look into the market, silicon MOSFETs can be found only in the range of, let's say, not more than 700, 800, or even 900 volt. So in this range, silicon MOSFETs already reached their limit. They're not so good performing. And therefore, we have to go to IGBT devices. And with silicon, we cannot build practical MOSFETs above, let's say, 700 or 800 volt. It's very difficult from the performance point of view. But with silicon carbide, it becomes possible to build MOSFET devices or unipolar devices even in the kilovolt range. I have seen numerous publications where MOSFETs are built in the, let's say, 10 kV or 20 kV voltage range. And this is possible because silicon carbide has a 10 times higher breakdown voltage. So this means that we can realize practical by unipolar devices also in the kilovolt range. So therefore, it's not anymore necessary to use only IGBTs, but we can also build silicon carbide MOSFETs in the high voltage range. So this is the main advantage of silicon carbide. How does this help us? I will explain in the next slide. And the third thing is, of course, silicon carbide has a higher drift saturation velocity, which means it can switch faster compared to silicon. And of course, this also has an impact on the switching losses. And one often discussed topic in literature is that silicon carbide has a higher thermal conductivity, which is true. Silicon carbide has 2 times the thermal conductivity of silicon, and therefore it can enable a better thermal design. Of course, this is true on paper, but in reality, this does not help much because in today's world, the silicon devices are anyways very thin. So the devices themselves don't contribute too much to the thermal conductivity. And the major disadvantage or challenge of silicon carbide is the higher defect density. So silicon carbide today is manufactured, or the raw wafer is manufactured in a different process compared to silicon. And this also makes the defect density quite high on silicon carbide. Of course, this is drastically improving over the years, but still it's not at the same level as silicon. And therefore, the size of the silicon carbide chips are rather limited compared to silicon devices. And also the price of silicon carbide is rather high compared to silicon devices. And I think this will remain at least for the years to come. Silicon carbide will be more expensive than silicon for the same chip size. But what we have to always keep in mind is the cost of the system. So if by paying more for the semiconductor, we can bring a major cost down on the rest of the system, then we will have to remember that the total cost of the system is lower. For example, with silicon carbide, if we can downsize the battery, then in the end, the system cost might still be lower, even if the module cost for silicon carbide is higher. Okay, so what are the benefits now of going from a bipolar to a unipolar technology? So a bipolar technology, the forward characteristics would look like the red line here. So this is from an IGBT. Current versus forward voltage, and we see that there is a threshold-like behavior, which means even when we have a small current here, the voltage drop is rather high. So whereas in a MOSFET, this is more or less a resistor-like behavior or a linear behavior, which means when you have a small current, the voltage drop is very small. But at a certain point, the losses of MOSFET cross over that of the IGBT, which means in this range, MOSFET is better compared to an IGBT because the conduction losses will be lower. And why is this important? I will show later that automotive traction inverters mostly operate in this region, even though they are designed for somewhere here. They operate in this current region. They operate in light load most of the time. And therefore, silicon carbide MOSFETs can bring a large benefit in terms of conduction losses. Okay, then going to the switching behavior. So when we go from a bipolar device, such as an IGBT, to a unipolar device like a MOSFET, first of all, we save on the turn off behavior. So if we look here, these are the turn off waveforms. So green is current and red is voltage in the rest of the slide. And dotted line is for the silicon IGBT. We see that the current does not fall straight away to zero, but rather has this decaying effect, or it's called a tail current. Whereas if you take a MOSFET, the current goes almost instantaneously to zero. So there is no more decaying effect on the, or tail current effect on the MOSFET. So this means we save some losses here. And this can be quite high depending on the technology of the IGBT. So this is the main, one of the major benefits of silicon carbide MOSFET. And the second thing is coming indirectly from the diode. I'm sure all of you know that when you turn off a bipolar diode, the current does not go immediately to zero. Rather, it goes in the negative direction and reaches a certain peak and then goes back to zero. So now all the energy in this, under this peak, this is a source of energy loss or power loss. So therefore, this has to be minimized. And this can be done by using either a silicon carbide diode or the body diode of a silicon carbide MOSFET. And in case of a MOSFET, this will be much lower. So this means we save this energy in a SiC MOSFET. And thirdly, we know that the reverse recovery peak of the diode also gets reflected on the active switch. So this means when you use a silicon diode, we also see this behavior on the IGBT. So this is causing losses also on the IGBT side. And we have to remember the diode recovery losses, they cause power losses almost twice, because it's happening in the diode as well as being reflected on the IGBT. So therefore we see the losses twice. And when we optimize the diode, we save also on the turn on behavior. So when we use a SiC MOSFET, either with the additional silicon carbide diode or with its body diode, the switching losses will be, or the turn on losses will be much lower. So the current peak will be lower, resulting in a overall saving in the switching losses. So this is why silicon carbide MOSFETs can switch much better. And also we could switch, for example, with higher slopes, which also brings down the losses drastically. Okay, then with this basis, I think we can go to the next part of the slides.
Yeah. Very good that you informed that. The last slide, all the questions were asked for me in the interview, all of them.
Okay.
So when I interview, so very good that you covered this. Very good. Yeah.
Nice
Please
to
go
know.
ahead.
Yeah, thank you. Okay, so then let's get into the investigation of silicon carbide modules. So once again, I show this Volkswagen ID. I like this car very much. I don't own it yet, but still, I like it from the spec. Okay, so now when we look at the powertrain of such a car, we see that if we look at the power loss distribution of this car, we see that roughly 45% of the losses are in the battery alone. And the next major contribution of the losses is coming from the traction inverter, around 30%. So therefore, this means that when we optimize the traction inverter, we can influence this 30%. So we can reduce the losses. And because the component is so large, we can have a major impact on the range of the battery electric vehicle. So therefore, we focus on this traction inverter application. Of course, someone might ask me, battery has 44% losses. Why didn't you focus on that? My interests were not so much on that, but I'm sure there is a lot of research going on in reducing the power losses in the battery. But the focus of this thesis will be on this orange component, inverter, 30% losses. Okay. So now let's look at the traction inverter application. Like I said earlier, this inverter converts or inverts DC of the high voltage battery to AC, which is needed by the electric machine. And the topology used here is a rather simple two-level topology here. So this is a standard in the market here. Almost, let's say 99% of the inverters in the market use this two-level topology because of simplicity, robustness, and also importantly because of cost. So today in the market, 150 kilowatt to 200 kilowatt, this is quite a standard power level for battery electric vehicles. So this is coming from the fact that when you drive an electric car, I think what is today a selling point or a major metric of the car is the acceleration from 0 to 100 kilometers per hour or 0 to 100 miles per hour. And this is a very important selling aspect. So you might have seen, if you've looked into car models, that they always claim 3 seconds from 0 to 100 or 4 seconds, 5 seconds, and so on. So in order to reach a certain level of acceleration, which is equivalent to today's combustion engine based cars, we see that this is more or less a power level which is required. So this is coming from the acceleration of the car. And the car has to be, or the inverter has to be designed to give a certain level of acceleration to the car. And the voltage level today, like I mentioned, we see mainly 400 volt. I think more than 80% of the systems are 400 volt systems today. But because of fast charging and because of range reasons, we also see that 800 volt systems are emerging in the market. And this switching, this inverter application is more or less, let's say, a low switching frequency application. Of course, depending on how you see it. So today we see more or less 10 kilohertz, 8 to 12 kilohertz as a operating switching frequency for traction inverters. So therefore, this will be the focus of this thesis. And the goal of this thesis will be to see what are the benefits of replacing these power switches from IGBTs to silicon carbide. And the goal will be to see what is the impact on the power losses or on the efficiency of the traction inverter. Okay, so of course, there has been a lot of work already in literature. Many people are still working on this topic. There are a lot of interesting things going on in the market or in the academia. But if you look at it, many of the applications or many of the publications, most of the work in the literature, this is focused on applications which are not so much or which are a little far from the real application. For example, we see very often that a lot of papers target inverters in the range of 50 kilowatt. Also sometimes high switching frequencies like 50 kilohertz, but we see that this is not reflected, or this is not reflecting the reality in the application. So therefore, these results are not 100% or directly applicable to the automotive traction inverter. Also, efficiency is considered only at a certain one operating point, but not over the complete drive cycle. So what is important for automotive is to consider the patterns of driving. So for example, one user might drive in a city, constantly accelerating, decelerating, and the efficiency performance will be very different from someone driving on the highway, where he's cruising at or he's accelerating a lot and then cruising at a certain speed. So the comparison is not fair. So therefore, it's necessary to consider over a so-called drive cycle or a mission profile. And this will be considered in this thesis. Second thing is, we see that many of the comparisons don't compare the devices in the same package. For example, I've seen some publications where large 300 ampere IGBT module was compared against a 65 ampere discrete JFETs put in parallel. Of course, I understand why they had to do this, because silicon carbide devices were really restricted on the market until a few years ago. And of course, this was a first step, but still it does not really compare the silicon technology versus silicon carbide technology, because here I would expect that there is also a large impact coming from the package, which is not so nice when we want to compare silicon and silicon carbide. And the third thing is that silicon carbide is typically or usually compared against older generations of IGBT. And this is also not a fair comparison because silicon carbide is a new technology and this has to be compared against the latest IGBT technologies. So therefore, in this thesis, we want to see what are the benefits when we replace silicon with silicon carbide without any influence from the rest of the system, either from the package, operating conditions, driver, cooling, and so on. So we want to see what is the direct comparison of silicon and silicon carbide from the technology point of view. And for this, we choose the latest state-of-the-art technologies. So I chose the micro pattern trench MPT IGBT technology from Infineon because this is the state-of-the-art today. And this was compared against the trench SiC MOSFET, which is also state-of-art. And I chose a package which offers very low or best-in-class strain inductance in the range of 8 nanohenry, which is today a state-of-the-art for traction inverter applications. And also the system and operating conditions are all kept identical to make sure that there is no discrepancy coming out of the system or the operating conditions. This will give a direct comparison of the chip technologies. And the second thing is we have to consider boundary conditions which are relevant today. For example, we know that the motors of the electric vehicles, they are restricted or the windings of the motors restrict the switching speed to less than 10 kilovolt per microsecond, maybe 15 kilovolt per microsecond. And this is a very this is a fact today. So therefore, we have to take this also into account. And also, so the first part was on boundary conditions that are relevant today. But then as a next step, we will also consider what happens when boundary conditions change. For example, what happens when the electrical machine is optimized so that we can switch faster than 10 kilovolt per microsecond and so on. Okay, so with this, let me explain once again the motivation. So the goal is to perform mission profile analysis. And to do this, we need a very accurate power loss model, which is most of the work in this thesis. And this power loss model also has to be capable of splitting the power losses into their root causes like tail current, reverse recovery, and so on, like I will explain. And this has to be experimentally validated. And when all these four parts or four jigsaw or pieces of the jigsaw puzzle are put together, then the goal is achieved. This is the motivation.
Yes, spectacular representation.
Thank you. Okay, so then what are the requirements on performing power loss analysis? What are the requirements of a power loss model? First of all, it has to be quick. The simulation has to be really quick because we have to simulate the complete lifetime of the traction inverter. And this is typically 8,000 hours today. So this is the operating lifetime of a traction inverter. And for this reason, it would not be practical, let's say, to simulate a switching point based simulation. It's not possible to switch or to simulate all the transients, but rather to use a closed form model of or a closed form of the model equations, meaning that we have an equation which calculates the power losses over a sine wave. So this is the main necessity of performing such simulations. And for this reason, I chose a behavioral power loss model for this thesis. And the accuracy of this model is very important. And I chose a target of plus or minus 5%. Why? Because if you compare two technologies today, typically we see that between generation 1 and generation 2, we see a roughly 20% improvement in the performance. And this means that if you have, for example, a model which has an uncertainty of plus or minus 20%, then we see that there is an overlap here. So we don't know if with such a method, if the benefit of a technology is coming really because of the technology itself, or is it coming because the power loss model is not accurate enough. So when we have a plus or minus 10% accuracy, then we see that there is no overlap. So therefore the minimum requirement is 10%, plus or minus 10%. But I chose a slightly further better step, which is plus or minus 5%. So this is the target goal for the, or the goal for the target accuracy of such a power loss model. And there are existing methods, for example, representations like this. But the disadvantage of this is that such methods, the coefficients are interdependent. And also they use linear approximations of the power losses, the switching and the conduction losses. So therefore, this is a little challenging. And secondly, also, if you look here, we see dependency on device current, junction temperature, DC link voltage, and so on. But there is no dependency on, for example, the gate resistance or the gate voltage, which can also have a large impact on the losses. And also there is no parameterization of the chip area. But normally we need to choose a chip area which is optimized for the mission profile. And this is not possible with such methods. So therefore, in the thesis, I proposed a method which takes these additional parameters into account. And again, if we model it like here, but with additional parameters, the coefficients are still interdependent. I will explain this in the next slide. Which is not so desirable. So which means that, for example, to build the parameterization, I would need to characterize at a large number of points. For example, I have to characterize the device at different collector currents, different junction temperatures, and so on, different voltages, and so on. So I would need to perform measurements at all of these points, which you see in this Rubik's cube. And furthermore, if I want to add the dependency on area, so AI is area of the active switch or the IGBT, AD is the area of the diode, and RG is the gate resistance. So if I have to add these three parameters, then the number of measurement points simply get multiplied. This means now I have to repeat all the, this entire cube of measurements over all these points. And now if I have to also add RG, then you see the matrix becomes really complicated. And this means that I will have a large number of measurements, which is not so nice. It will make the life of the person who's performing these measurements really difficult. So therefore, in this thesis, I proposed a method which uses independent coefficients, which means that I model the switching and the conduction losses as product of different functions. So the difference here is that here it's one function of different parameters, and here it's a multiplication of several functions, and each function is independent of the other parameter. For example, the function on collector current can be determined independent of the DC link voltage, and so on. So this makes it really practical for mission profile analysis. I will have to pay attention to time. I think we are running out of time, right?
Yeah. It's fine. It's fine. Please, yeah. Go ahead. No
Okay,
problem.
thanks. Please let me know if I'm consuming too much time.
No. Please, yeah, go as detailed as possible. Not
Okay,
an issue.
thank you.
Time, not an issue.
Thank you. Then I will take that privilege.
Yes. Please do.
Okay. Okay. So then, so what we do is in this approach, we define nominal points for or nominal values for each of the parameters, like you can see here. So I define, for example, for the collector current, 450 ampere as the nominal point, DC link voltage 400 volt as the nominal point, and so on. So this means now I don't need to look, or I don't need to characterize all of these Rubik's cubes. I can look only into the Rubik's cube, which is represented by these nominal points, which is this. And even within this Rubik's cube, I don't need to characterize all the points. I can look into, for example, what I do is I keep all the parameters at the nominal values, but vary only one parameter at a time. For example, here, I vary the collector current of the device, keeping everything else constant. And then I do the same at different DC link voltages, keeping everything else the same now. and then I do the same at different junction temperatures. So the advantage is within this cube, I would need only 3 rows of measurements. I don't need the complete Rubik's cube. And similarly, when you go out into this bigger matrix picture here, I wouldn't need, for example, this complete Rubik's cube here, but rather I would need only a few points outside, which are these here, where I vary only the chip area, the diode area, and the gate resistance. So anyways, not to complicate things too much, what I do is in this method, what is done is that instead of measuring at all points, we do only at certain points which are necessary for getting the complete accuracy of this model. And this means I would need only so many number of measurement points. If you remember in the previous slide, I showed that we would need m times n times so on. Here it's replaced by a plus, which means the number of measurements are significantly reduced. But the accuracy of the model is still very good. So even though I have not characterized any point in this cube here, if you can still see my pointer.
Yes, we can.
I can still calculate with this model what are the losses here with a very good accuracy. And this has been verified in this work. So this is the advantage of this model.
Yes, one quick question, because this slide
Yes.
has a lot of information.
Yes.
So do you prove along the way somewhere else that this accuracy is good enough? Do you take some other points and show that this was good enough compared to taking all the points? Do you show that anywhere?
Yes. I will come to that.
Okay.
That's a very good question. I was expecting it, but I will come to that later.
Good.
Okay, so just to summarize now, this is the approach chosen for the thesis, where we model as a product of six or n different functions, and each function is independent of each other. Okay, so now coming to the next one. So I was talking in the beginning already about mission profiles or a drive cycle. So in case someone is not familiar here, maybe just a couple of sentences. So drive cycle, for example, is a table of speed versus time, which indicates what is the driving pattern of the user. So automotive companies use these mission profiles to brand or to design their car. For example, if you buy a car, if you buy it in Europe, you will normally see what is the carbon dioxide emission of a car over the NEDC or the WLTP mission profile. So these are all mission profiles. It is only used to benchmark and, let's say, define or well define the driving pattern. Because otherwise, if there are no mission profiles, each car manufacturer would specify the energy consumption or the CO2 emission at their own, imaginary points. So in order to prevent this, there are mission profiles. There are several mission profiles in the literature, but I will consider just a few. So this is a mission profile which we see practically on automotive inverters today. I've taken this from our internal or from a practical case. And this is for an inverter which is rated for 450 ampere. So the nominal rating of the inverter is 450 ampere. But if you look at so on the x-axis is the RMS current, and on the y-axis is the operation time. So this is a histogram of a mission profile for a typical city. And if you look at this, you see that even though the inverter is rated for 450 ampere, we are operating greater than 300 ampere less than 1% of the time, right? Because in the city, we are typically accelerating for a short time and then immediately decelerating, right? Even if you accelerate fully, you cannot drive. I mean, for example, in Europe, you cannot drive more than 50 kilometers per hour in most of the city. And you can drive only above 50, mostly on the highway or on the country roads and so on. So therefore, this for a city mission profile, you will see that more than 300 ampere is less than 1% of the total time. Whereas less than 100 ampere of the time or 100 ampere of the current is more than 95% of the time. So for me, the conclusion or the message is that the conclusion is that the inverter is operating more than 95% of the time at less than 1/4 of the nominal current. So this means that the inverter or the automotive traction inverter has to be optimized for this region, because this is the most operating point in the inverter. And if you remember a few slides back where I showed the IGBT versus MOSFET behavior, we have to recollect that the silicon carbide MOSFET is especially better performing in this light load condition, which is very good for the traction inverter. So therefore, silicon carbide MOSFET offers a very good performance in this region, but we will anyways verify it later. And so this was the question from you. So have we compared the error or the accuracy of this method? Yes. So what we did is we calculated the percentage error with two methods. So the red is using the existing methods which you saw on the left side a few slides back, and green was with the proposed method which you saw on the right side, which was used in this thesis. And we used a benchmark method to compare these two methods. So and the benchmark method is actually considered characterized at all the Rubik's cube points. So basically we have measurements at all the points, and then we compare what are the losses calculated by these two methods. So here you will see percentage error compared to this benchmark method. And we see that if you take the nominal point, right? Sorry for this. If we look at the nominal point, the percentage error is very low for both the methods, right? Both existing and proposed methods offer close to, let's say, 1% error. But when you go to low current points, we see that the percentage error of the existing methods increases drastically. And this is because the existing methods are normally optimized for the nominal point, which is where dimensioning is done. And I fully understand why these methods are optimized for the nominal point, because the goal of such methods is to dimension the inverter for the nominal point. But this is not suitable for mission profile analysis, because like we see here, the mission profile is mostly in the light load region, and therefore such a method would not be suitable. Which is exactly why we proposed the method that I showed in the last 3 slides. And with this method, we can see we are close to less than 2% error, even in the light load condition, which is a significant improvement. And this means the message is that with the existing methods, we are calculating close to 20% error here for more than 95% of the time. Whereas with the proposed method, we calculate less than 2% error most of the time. Okay, hope I have answered your question at least partially.
Yes.
Okay, thank you. Okay, so then let's go ahead. Okay, the second part is, I mean, so far I know that, or so far we can calculate what are the total power losses of the inverter, right? We could also see what is the contribution due to switching, what is the contribution due to conduction, and so on. But what we cannot still do is to see what is the contribution due to the tail current, what is the contribution due to the reverse recovery, and so on. And for this, a method was proposed in this thesis which can make it possible to split the losses based on the root causes. I mean, if you look here, it's a little complicated plot to explain in a short time. I will try my best.
Take your time. Take your time. We have the time. Yeah, take your time and do justice to the plot. No problem.
Okay, thank you. Thank you. So if you look here, blue is the current waveform. So this is the turn off event of the IGBT or MOSFET. So blue is the current waveform at turn off, and red or orange is the voltage waveform. So we see that the current is at full load here, and then it falls to 0, right? And the voltage is at 0 when the device is conducting, and then it goes to the bus voltage. So this is the turn off event. And if we look here, we see already that there are, let's look only at the blue waveform, okay, to avoid confusion. Let's look only at the current waveform. If we look here, we could already split it into 3 parts, A, B, and C. So A is due to the capacitive part. We see a small dip here, which is coming because when the voltage across the device is rising, it means we are charging the capacitance, right? And this charging of capacitance has to happen from the load current. And this dip is due to this load current, or a part of the load current which is charging the capacitance. And the second part is where the actual commutation is happening between the high side switch and the low side diode. And the third part is due to tail in case of an IGBT, which we see here as a dotted line. But in case of a MOSFET, like I explained, there is no tail. So we don't see this part here. So with this method, it is possible to calculate the energy separately. Normally, what would be done is to calculate the energy over this complete event to tell, for example, that the total energy in this event is 10 millijoules, for example. But with this method, it is possible to split it further into three parts. I can tell that, okay, the energy due to capacitance is 5 millijoule. Due to the commutation is 10 millijoule, for example, just as an example, and due to tail is 5 millijoule. So this is possible with this method. And another thing to notice is the DVDT is in the region A. So this is due to the capacitance as well as the DVDT. And the DIDT, or the slope of the current, is mainly in this region B. And C, like I said, is the tail current. So this means this method makes it possible to split the losses based on capacitance or DVDT, current or DIDT, and tail current. So based on this, and with this method, we could see, for example, let's look only into this part because I think the plot is very complicated. So on the y-axis, we see the turn off energy, and on the x-axis, we see it for three different devices. So the first device we see here is full silicon. I will use this term more often also in the next slides. So it's better to explain this a bit in detail. So this is IGBT, or silicon IGBT plus silicon diode, which is used very widely in automotive inverters today. In the second device, it's a hybrid silicon carbide device, meaning that the IGBT is the same as this IGBT, just the diode is replaced with the silicon carbide Schottky diode. And the third device, it's a MOSFET, and the MOSFET already has a body diode inside the structure. So we don't need an additional diode outside. Okay, so these are the three different devices. So now I could compare at this 300 ampere operating point, what are the contributions due to the three different parts. So the part A that you can see here, this was due to the capacitive effects. Or before that, let's look at B, part B. So we see that the contribution due to part B for all the three modules is nearly the same, right? Almost the same. This is because for my comparison, I have considered that the modules, or I have considered points where the modules are switching nearly at the same speed or same DIDT. The contribution due to region A, this is the contribution due to DVDT. Okay. And I could do a similar thing by, instead of comparing at same contribution due to region B, I could do it at the same contribution due to region A, which would mean then I'm comparing at the same DVDT. And C is the contribution due to the tail, which we clearly see is missing in case of a MOSFET here, right? So this is what I was mentioning. But just once again, to summarize this method, we could split the power losses or the switching losses into their root causes to see what is the contribution due to the DVDT, due to DIDT, and so on. And I could always see what happens when I keep the DVDT the same and then optimize the other system and so on. So it's possible to make such kind of studies with this method. Okay, then quickly on the validation. So far we had, or I showed some models which were proposed in this thesis. And of course, simulation model is a simulation model. We need to always verify it before, before we can trust the results of the model. And for this, the method was experimentally validated. So two methods were used. I mean, it's always good to, for validation, it's always good to do it with two independent methods, because if you do it with one method, then you don't know if the measurements are wrong or if the simulations are wrong. So it's always good to have two independent methods to validate. And therefore, I used firstly an electrical method, which is using a power analyzer. I think most of you are familiar with this.
Yes.
And right, so basically what we do is we measure the input DC power, which is very easy to measure, and also the output AC power. And the difference of these two should give the power losses in the inverter, right? So this is a simple, quick, and a well-known method, but there is a very important thing here. The output of the inverter, right? This would look, the voltage waveform would look like this. So this is very far from a sine wave. Even though the current waveform is more or less nicely sinusoidal, the voltage is not at all sinusoidal. It's switching, let's say, with a lot of transients here. And if you look at the frequency spectrum of the output waveform which was measured, we see that this is the fundamental here, right? We see there is a very large component at 2 times the switching frequency. So switching frequency was 8 kilohertz here. So we see a large component at 16 kilohertz, which means that there is a lot of noise, and this will have a high impact on the power losses that we measure here. Okay, I have seen also at some points that the efficiency was more than 100%. So I can tell you that there is a lot of error in this method, depending on the operating points. So therefore, we also wanted to use a second method to, okay, I will come to this maybe later.
Yeah.
Okay, so here is a comparison of the losses measured with the power analyzer based method and simulation. And we see that there is a good overlap, right? We also see, I mean, if you look here in detail, okay, let's take this point. We see that the brown curve, which is the simulation, it's lying within the uncertainty of the measured method. So this measurement method has an uncertainty of plus or minus 20%. So this was calculated based on the information in the manuals of this Yokogawa power analyzer, and already we reached plus or minus 20% or total 20% uncertainty.
So what do these vertical lines at each point mean? 100, 200, 300, 400?
Yes. So this, right, you mean?
At 100, you have a vertical blue line. 200, you
Yes,
have
yes.
a...
Yeah. Okay. So then, sorry, I did not explain this. So this plot, first of all, shows the power loss as a function of RMS current. Okay. And there are two lines here. First of all, ignore please the vertical line for now. So there
Okay.
are two curves, the blue curve and the red curve. So red curve is the simulated and the blue curve is the measured one. But on the measurement, right? Of course, the measurement is not exactly, I mean, when you measure 100 watt, right? It's not exactly 100 watt because the measurement or the measuring instrument has a certain tolerance or uncertainty, right? And this can be calculated systematically with the help of the manuals of the measuring equipment. And with this, I calculated this uncertainty. So this means even though the measurement device is measuring at this point, it could be anywhere between this limit and this limit. This is the uncertainty. Okay.
Got it, got it, got it, got it.
Okay. So this means that there is an uncertainty of plus or minus 20%.
Got it.
So this
It's like
means
the tolerance of the scope, sorry, the analyzer itself. Okay.
exactly.
Okay.
So I was calculating this. So I mean, the complete calculation is there in the thesis, but I did not include it too much here. But
Yeah,
we
but
see that
is this common to take into account? Because I'm seeing this for the first time, where you're taking the tolerance of the measurement instrument into account. Is this common nowadays? Common, or you have considered it?
yes, I mean, I see if you look at a lot of literature, right, this is not taken into account, but I think this should be taken into account.
Got it, got it.
Because let's say I measure with the same device, right? At one point of time, I might have the I might have the measurement here. And if I measure it the next day, right, same device, same equipment, everything is the same, I might measure here because there is an uncertainty in the method, right?
Got it, got
And
it.
this might mean that if I measure it today, I might see 10% high losses, and tomorrow someone else measuring it might see 10% lower. So therefore, we have to always know what is the uncertainty of the method. And this is, I mean, for me, using this measurement method, right, it doesn't make sense to compare something which is in the range of 20%. Because the measurement method itself has this tolerance of 20%.
Understood.
Yeah. Okay. So this is the thing. But if you look here, the message is that the simulation is still within the, the tolerance of this measurement method for almost all the points, from light load all the way up to nearly nominal current. Okay. So the,
Yes.
okay, so two messages. One is simulation is matching the measurement. I mean, this was the main goal for us to verify the measurement method. And the second thing is that also this measurement method based on power analyzer, right? This has a high uncertainty, which could be in the range of 20% at light load. So this is the message. So this means that the standard power analyzer based method, it's good to measure with this method, but it is not sufficient to validate the power loss model. And therefore I need a second method to measure. And the second method was developed as part of this thesis. So this is a calorimetric method. And the focus of this method was the light load condition, because we see here that the main, bottleneck is the light load condition, right? Because for the automotive traction inverter, this is the important point, like I showed in the previous slides.
Yes. Below 100 amps. Yeah.
Exactly. Yeah. So therefore, this method is based on or optimized for light load condition. The advantage of this method is that I don't need really complicated or expensive measurement stuff or measurement equipment for this. So what I do is, so this is a power module. So I think if someone is working on this power modules, they will know what I mean here. So what we do is we inject, or firstly we isolate the base plate. So this is this brown portion you see here, right? This is the heat sink of the module. So automotive power modules typically already have some heat sink attached to the module. And this is the heat sink that I'm referring to, which is already part of the module. So if someone is buying the module, right, they get this system.
Okay.
What we do is we insulate this base plate, meaning that heat cannot now go out of the base plate, but is more or less trapped inside the system. And then we inject a known level of power into the diodes. So by known, I mean we inject DC power, because DC power is very easy to measure. I mean, it's a constant waveform of current and voltage, right? It's very easy to measure. So I inject DC power, which is known and calibrated, and then I see what is the temperature rise of the base plate for a known power. And I do this at different points. Okay, so I have a calibrated curve now. And then I inject the unknown inverter power. I don't know what is the power loss, but because the rest of the system is the same, right? I can still use the temperature rise to back calculate what was the injected power. This is the idea of this method.
Very good. Very cool. It's like perturbation, DC power perturbation. Yeah.
Yes.
Very good. Yeah.
So the advantage of this method is that, I mean, I'm not measuring the losses, let's say electrically, right? I mean, I'm measuring the losses. I'm sort of capturing the thermal losses.
And then the losses.
Yes. So there is no impact. I mean, this method would be independent if, the inverter power applied here had a lot of oscillations, because what is ultimately being measured is really the heat. Whereas in the other method, it was not the heat. It was the difference of two powers. And this had a lot of impact on the, or impact of the high frequency components.
Yeah. Very intelligent way of doing it. Good.
Thanks. So this has the advantage that there is no impact of switching frequency. And second thing is also, like I will show later, it has a higher or a lower uncertainty, especially in the high load condition. So now just to recap, if you remember from the power analyzer method, right, we had this picture on the left, right? So we had this at 100 ampere, we had this point.
Yeah.
Okay. So now with the calorimetric method, we see that, I mean, we don't see the complete picture because this method is restricted. I mean, this method is optimized for the light load. And because I am sort of not cooling the module, right, I cannot measure at higher RMS current points. So this is a limitation of this method. But anyways, because I wanted to look into the light load, this is sufficient for me. And here, again, we see two lines. So brown or red is like here, the simulation. And we also see a blue line. I mean, the blue line is hidden behind the red line because they're overlapping quite nicely. But let me zoom in. So I'm taking, once again, the same point, 100 ampere point, like here. And what we see here is, first of all, the red line or the brown line is very close to the blue line, right? So the simulation is matching quite well to the measurement. But also what we see is the tolerance is now significantly lower. It's the same scale for the two bubbles here.
Got it.
This is more or less 5%. So this means with the calorimetric method, we have a better or a lower uncertainty at light load.
And what is the temperature sensor you're using for the calorimetric method? How do you?
Yeah. So firstly, this is an advantage of the method. It does not depend so much on the temperature sensor, so long as I use the same sensor. So for the module, right, what I did not show here, just to make it simple, was the NTC, or the negative temperature coefficient resistor, which is typically part of power modules for inverter applications.
Got it.
So that would lie somewhere here on the substrate, and it would measure close to the chip temperature. But you could also, for example, insert a thermocouple either into the base plate or better close to the chips, and and perform this method. It does not really depend too much on the sensor itself. Of course, the accuracy of the sensor should be good. Otherwise, we will see that this 5% might be higher. So you might have 10% instead of 5%. But
Because
the method can be principally used for any kind of temperature sensor here.
Understood.
Okay, then okay, so then so now we have a good level of trust on the simulation method. So you can trust the results that I show in the next slide. Okay, so now what we do is we compare the average power loss on the y-axis for the three different technologies that I showed. I hope you still remember the full silicon, hybrid silicon, silicon carbide, and the full silicon carbide. Okay. So what you see here is the average power loss over a mission profile. So this is not at one operating point, but rather over a drive cycle. So someone is driving a car on a highway with a certain behavior, and then we simulate the average power losses over this time. Okay. So these are the boundary conditions here. So this is a 400 volt system. Like I said, this will be the focus. Switching frequency is 8 kilohertz. And now we see the hybrid silicon carbide module, right? This has a 25% lower losses because with the silicon carbide diode, the reverse recovery losses are reduced or almost disappeared even. And with the full silicon carbide module, we see the power losses are reduced by 60%. Okay, so this is what we calculated. But of course, I mean, this alone is not so impressive, or it does not tell us too much about the system, right? We would like to have some more details. And for this, or this is where the commutation-based method to split the power losses comes into play. So we can now look also what are the components due to different, different root causes. For example, so this green contribution is due to the conduction losses in the forward direction. So basically the active switch. And if we see here, right, there is not so much difference between the first two. Why? Because the IGBTs are the same for both. So it is nearly the same. Maybe we see a small difference because of measurement tolerances in the characterization. But when we use a silicon carbide MOSFET, right, we see the losses are reduced significantly, right? Why is this? Because if you remember now, um, this is what I showed earlier. So we
Yes.
are operating mostly in this, somewhere in this region, where the voltage drop of the MOSFET is much lower than the voltage drop of of an IGBT, right?
And this plot is for a fixed frequency, right? The one
This is
on
a
the
fixed
one.
frequency,
Okay.
yes. And then the losses due to reverse recovery, I mean, due to conduction, but in the reverse direction, which is basically the power loss of the diode. Okay. And here we see that the silicon carbide diode, right? This has a slightly higher losses than the silicon diode. This is because silicon carbide Schottky diodes have a larger voltage drop compared to the silicon diode. They're not so good in terms of conduction. And this is coming actually because of the higher band gap. But anyways, so it's a trade-off. And in case of the silicon carbide MOSFET, right, the advantage is you can also use the MOSFET in the reverse direction. So silicon or any MOSFET in general can be used in both directions, forward and backward direction. And in the backward direction, it has a similar behavior, linear behavior. So we also save energy losses in the reverse direction. And this is quite large because also the diode, right, it has a IGBT-like behavior with this threshold voltage. So this was about the conduction losses. Second thing now is the diode reverse recovery. So we see that already when we go from a silicon diode to a silicon carbide diode, right? We save a lot on the reverse recovery here. I mean, it's a factor more than 20, let's say factor 3 reduction or factor 4 reduction, right? And we see similar behavior also for the silicon carbide MOSFET. Because I mean, the silicon carbide diode here, right, in the second bar, this is anyways a unipolar diode. There is no reverse recovery charge. But in case of us, sorry?
Yeah. Just one question. Did you try this at any other frequency apart from 8 kilohertz? Do you show that
Yes,
in your thesis? Okay.
yes. You are kind of predicting what is there in the next slides. This is there in the next slide. I will show this.
Yeah, please go ahead.
Yeah. So we also see that with the silicon carbide MOSFET, right, we can reach nearly the same behavior as with the silicon carbide diode, as far as the diode reverse recovery is concerned. Okay. And the next thing is, like I mentioned, when you change the diode, right, you don't save only on the diode, but you save also on the active switch because the recovery peak is reflecting on the IG or the active switch. So therefore, we see a saving also uh, on the active switch side. So this green portion is due to turn on, the recovery part of the turn on waveform. And we see that also here there is a significant saving, right? So now what is missing is finally the tail. So we know the IGBT has a tail current, which is missing in case of a SiC-MOS. But in case of a hybrid device, it is still existing because we are using the same IGBT, right? We change only the diode and tail current is not affected by the diode. So therefore, we see already we are saving quite a lot of power losses by using a silicon carbide MOSFET. And what is to be also, let's say, stressed a bit here is that these savings are coming because we go from a bipolar device, such as the IGBT, to a unipolar device like the silicon carbide MOSFET. And we would get this saving irrespective of how fast we are switching or, what is the DVDT, DIDT, and so on. This is coming simply because we go from an IGBT to a MOSFET. Now comes the remaining part. So if you remember in the turn off waveform I showed, right, there was a region A, right? Region A, B, and C.
Yes. Blue curve. Yeah.
Yeah. The region A was due to the DVDT or the slew rate of the voltage. How fast is the voltage going down, right? And here, if you see, this is more or less the same for all the three devices. which means I have taken care to see that the devices are switching at similar speeds as far as the DVDT is concerned. Why did I do this? Because no matter what switch you use, as long as you have an electrical machine which is limiting the switching speed, right? So today the thing is electrical machines, I mean, all electrical machines have windings which have some insulation. And today the insulation is limiting the switching speed to less than 10 kilovolt or 15 kilovolt per microsecond. So if you go higher than that, right, then you induce capacitive currents in the insulation, and this will destroy the insulation of the machine. So even if you have a very high speed device, very high performance device, you cannot switch more than 10 kilovolt per microsecond, because if you do, you will kill the machine. So therefore, it doesn't make sense to now switch the SiC MOSFET so fast that you kill the electrical machine, right? So therefore, I have ensured to compare at the same DVDT.
And there's no concept of snubbers, right? You are making. Oh,
I have not used snubbers, but it's a very valid question, because when you use snubbers, you could save partially some of the losses. Some of the losses get transferred from the device to the snubber, but still you could save some part of the losses. But I have not considered it here, because if I use a snubber, right, I could use it for all the devices. So this is the contribution due to DVDT, and this is nearly the same for all. There is no saving because I'm switching at similar DVDT. And the next is the contribution due to the DIDT part. And also this, if we compare, right? So blue is DIDT at turn on and brown is DIDT at turn off. And we see this is more or less the same for all three devices. This is also, again, because I was switching the devices at similar DIDT.
Good.
So if you see here once again, 75% of the total losses are coming mainly because of bipolar effects, like tail current, like recovery, and so on. And only 25% of the losses are coming because of switching faster or slower. So even if, let's say, you switch the IGBT really fast, right? You can influence mainly only this 25%. The others will remain more or less the same. Of course, when you switch faster, the reverse recovery will actually increase, but you can influence mainly this 25%. So even if you switch an IGBT very fast, right, you will not be able to influence this big 75%. And for that, we need to go from a bipolar device to a unipolar device. So this is the message. So first of all, SiC MOSFET brings down the losses by 60%. And this comparison is at the same or similar DIDT and DVDT, which I think is very fair. And second, most of the benefits are coming because we are going from a bipolar device, IGBT, to a unipolar device or a SiC MOSFET. And this is very important, I feel, because in literature, we see a lot that the benefits of silicon carbide happen or occur because we switch the devices very fast. But I think this is not really true. Partially true, but not fully true. So therefore, it is not very important to switch a silicon carbide MOSFET too fast to get its benefit. You will still get some benefits of SiC MOSFET, and this could be in the range of 60% for this particular application. Purely because you are going from a bipolar device to a unipolar device.
Understood.
Okay. So then if there are no further questions here, I can go to the next slide.
Yes. Please do.
So this is more or less the last slide of this presentation. It's a bit complicated, but I will try my best to explain it. So even if you don't follow 100%, I think if you catch the key messages, I think it's good enough, because it would take a lot of time to summarize this plot. So what I did here in the previous slide, right? This was for one mission profile, right? This was for Artemis mission profile, for a certain highway mission profile. And this was for 400 volt. This was for 8 kilohertz switching frequency. Just like you asked me, what happens when we go to a higher switching frequency, right? Someone might also ask me, what happens if I go to 800 volt now? Do you expect similar benefit, or what happens when I go to a different mission profile? So instead of a highway mission profile, if I use an urban mission profile, right, or a city mission profile, do I get the same benefit or not? So in order to explain or answer that, I have this plot. So here, what I show is basically, you see two circles, right? Not exactly circles, but one inner circle and one outer circle, right? So inner
Yes.
circle is the reference point. So this is the performance of the full IGBT device or a full silicon device. So it is this device, okay, the reference device. I take this as a reference now, full silicon.
Got it. Got it.
And green shows me what is the improvement offered by the hybrid device compared to the reference device.
Understood. Understood.
And the purple tells me what is the improvement offered by the full silicon carbide device compared to the reference device. Okay, so just as a link from the last page to this page, if you look here, we had 25 and 60% benefit, right, compared to the IGBT module. So we see it here. If you look here, right, so the scale is, the inner circle is 0% and the outer circle is 100%. So if you look here, the green dot is roughly 25%, which means it offers 25% improvement or 25% benefit compared to the reference module, which is the full silicon. And this is 60%, as you can see here, right?
Understood. Understood. Yes. Yes. Yes.
Okay. So now what we will do is, instead of the highway profile, right, what might happen when we go to a different mission profile? So let's say we go to an urban mission profile or a city mission profile. So we see that the benefits are of silicon carbide are actually increasing, right? I think
Yes.
we can ignore the green one. We can look only
Yeah.
at the purple one. So the benefit of the full silicon carbide module is improving, right?
Yes. Yes.
Why is this? Because if you look at the plot here, when you go to lower speeds, right, you're moving the point further lower, where the silicon carbide MOSFET has a much better advantage. So
Understood.
therefore,
Urban, because of urban profile. Okay.
yes, right? So this means the benefit of silicon carbide is higher at lower vehicle speeds. I think it's important not to confuse here with the device switching speed, but at lower vehicle speeds.
Yeah, you're very focused on urban cycle below 100 amps. So I think yeah, it
Yes,
makes sense. Yes. Yes.
yes. And the second thing now, okay, let's take now this point here. So what you see here is the urban mission profile. And now what happens, for example, so here, like you remember, I was considering that the DVDT, DIDT is similar for the three modules, right? And the DVDT was in the range of 10 kilovolt per microsecond, max DVDT. So now what happens if I restrict, for whatever reasons, the DVDT to less than 5 kilovolt per microsecond?
Got it.
Yeah, you see that there is not so much change. Of course, there is a bit of a change, but I think this is very insignificant. Why is this? Because if you remember from the last slide, the contribution due to the DVDT and DIDT is not so high, right? Most of the contribution is coming from the bipolar effects, which have nothing to do with or not so much to do with the DVDT. Okay. Now what happens when, for example, I switch the devices as fast as possible? Let's forget that there is an electrical machine which is limiting the switching speed. Let me switch all the devices as fast as we can. And we see that in this case, okay, the benefit of silicon carbide is slightly higher, but still it's not a big step, right?
Yeah.
It's a small step. This is again a confirmation of this discussion in the last slide. And next, what happens when the switching frequency is increased to 20 kilohertz? So this was your question, right?
Yes.
So we go from 8 kilohertz at this point to 20 kilohertz at this point. So of course, the benefit of silicon carbide is more at 20 kilohertz because, you know, switching losses become more dominant. And because silicon carbide can reduce the switching losses, you will see a higher benefit. So therefore, benefit of silicon carbide is clearly higher at higher switching frequency. But today, automotive traction inverters, they are mostly switching in this range of 10 kilohertz. And I have rarely seen someone switching much higher than that, maybe 12 kilohertz, but not 20 or 30, 20, 30 or 40 kilohertz. Why? Because the more the switching, the more the switching frequency, right? The higher will be the switching losses. And therefore, it does not bring anything much to the system. Only it only brings a higher switching loss or a lower efficiency. So therefore, most OEMs or most manufacturers will not go for a higher switching frequency than let's say 12 or even maybe 15 kilohertz.
And all are hard switched, right? Hard switched. Okay.
Hard
Okay.
switched. Yes.
Yeah.
Okay. Then let's look at what happens at higher temperatures. Okay, so far we were discussing the average power losses, right?
Yes.
So now we will change it a bit and we will discuss about the total chip content or the total semiconductor content I would need in a module for a given mission profile or for a given operating point. Okay, so now if I dimension a silicon carbide module for 125 degrees Celsius max junction temperature, right? Then the silicon carbide module could be half the size of an IGBT module. I mean, it could offer like 50 to 60% saving in the chip content, meaning that for an IGBT module, if you need something like 300 square millimeter, right? With the SiC module, you might need 150 or maybe 120 square millimeter. But
so do we have the capacity to select it, die size, or
yes,
okay.
yes. I mean, in the model, yes, because like I mentioned, right, this model parameterizes even in terms of chip size.
Got it.
So I can already see, okay, if I reduce the chip size by factor 2, what will be the impact on efficiency and so on. I can already do it with the method. So now what happens now instead of restricting the junction temperature to 125 degrees Celsius, right? What happens when I restrict it to, let's say, 175 degrees Celsius here? So we see that the benefit of silicon carbide goes down actually. So you would, instead of 50% lower chip size for silicon carbide, right? Now you will have only 30% lower chip size compared to silicon. And like I said, silicon carbide is for the same area, right? Silicon carbide is not the same cost as silicon. So there is also a cost or price difference. So therefore, you know, as we go to higher temperatures, right? Let's say we go to 300 degrees Celsius. This is purely a, let's say, theoretical point. Because silicon cannot really go above 300 degrees Celsius. But anyways, just as a hypothetical case, right? Let's say we can go to 300 degrees Celsius. Then we see that silicon carbide would need more chip area than IGBT, which is then, you know, it will not be commercially attractive at all. So therefore, the message is that going to high temperature, right? This is not really benefiting silicon carbide. And this is quite contradictory to what you might find in literature, because in literature, you see that higher temperature is always good for silicon carbide.
Higher junction temperature, TJ.
Higher junction temperature, yes. So the gap between silicon carbide and silicon, it becomes narrow at higher temperatures. And how do I explain that? Once again, I will explain it with respect to this picture. So what happens when you, you know, dimension a module for a higher junction temperature for the same chip area, right? You can allow a higher RMS or a higher current in the device, right? So the current or the current which the module can take at 125 degrees Celsius or at 300 degrees Celsius will be much higher than what it can do at 125 degrees Celsius. So this means on this graph, it moves to the top. The operating point moves to the top. And here we see the MOSFET is not so good compared to the IGBT. The power losses are higher for the MOSFET, at least as far as conduction losses are concerned.
Got it.
So this is why high temperature operation, you know, it's not 100% beneficial for silicon carbide. Okay. Then last thing is the current or the power capability at different voltage levels. I think this is very important because like I mentioned, right, even though today we are at 400 volt, I see a clear trend to go to 800 volt in the future. So there will be more and more 800 volt systems in the market. And therefore, we have to see what is the benefit of silicon carbide at 800 volt. So far, we only saw at 400 volt. So now what we do is we check what is the current or power capability of the module, meaning that for a given module size, can I draw 300 ampere from the module or can I draw 500 ampere from the module? It's best when the module can give me more current capability.
Understood.
So at 400 volt, silicon carbide can give roughly, let's say 25% more current capability. But when I go to 800 volt, this goes up by to roughly 60% or even 65%, which means the benefit of silicon carbide is much higher at 800 volt. Why is this? Because IGBTs are not so optimum at this voltage class. So for a 800 volt system, right, you would need a 1200 volt IGBT.
Yes.
And in this voltage class, IGBTs are not so attractive because they are bipolar devices, right? And the breakdown voltage has a direct impact on the drift region, meaning that a 1200 volt IGBT, right, it would need a thicker drift region compared to a 650 or a 750 volt IGBT. And therefore, you will have more bipolar charges and so on. And therefore, you will see more switching losses in the device. So therefore, at 800 volt, silicon carbide becomes more attractive. So to summarize here, we saw that silicon carbide MOSFETs improve efficiency performance by more than 2 percentage point, meaning that you go from something like 96.5 to 98.5 efficiency. And the impact on the driving range was in the range of 5 to 10%, again, depending on the mission profile. Okay, so with this, I go to the conclusions. So the goal of this thesis, like I said, was to compare silicon and silicon carbide 1-to-1 for the traction inverter application from the point of view of mission profile efficiency. And this we did. For this, it was necessary to come up with a power loss model which is accurate enough to see the difference in the technologies, and which is also capable of splitting the power losses into different components. And we saw that most of the benefits of silicon carbide, right, come because we are going from a bipolar to a unipolar behavior. And in future, I think it would be a nice area to, let's say, add the influence of electrical machine, passives, and so on in this thesis. This was not in the focus of the thesis, but it would be nice to see how does the inverter behavior to behave together with the electrical machine. I think this would be nice to see as a future work.
Okay, okay. Very good, Ajay. Yeah, please go ahead.
Thanks a
we
lot.
have lots of questions. If you could just stay, we have lots and lots of questions. Karthik, can you please go ahead, unmute yourself and go ahead, Karthik?
Yeah, Ajay, hi.
Yeah, please go ahead, fast.
Yeah, so I had two questions. Like, one was like, why didn't you consider double pulse testing actually? Like, isn't it the standard testing methodology to get the switching losses? Like, you used calorimetric method and you used power analyzer method. Maybe you could get way better curves from double pulse testing, you know, like, and it could be way better matched. Was there a certain reason actually?
No, I mean, I fully agree with you that double pulse is a state-of-the-art method to parameterize losses. And in fact, this is what I meant. Maybe I was not so clear in the slides, but this is what I meant when I said switching energy here. So by characterization, I meant that we perform double pulse measurements here. So each of the point here, right? This is actually a double pulse measurement.
Oh, it was already done.
It was already done.
Okay.
So if you look here, right? So switching energy is measured at so many points, and
Yeah.
at each point I have to run one double pulse measurement.
Okay. Okay.
And this means if I have to measure at so many points, right? I think if you have performed double pulse measurements, right? You know the pain in performing it, especially if you have so many measurement points.
Yeah, yeah, that's true. But usually, like in my experience, what I learned was like it's painful, but it gives you more accurate results than many other methods.
Yes. Yes, but anyways, so the basis for this work was double pulse measurement. So all the points here, right? These were measured on a double pulse setup.
Yeah, yeah,
Okay.
I get it. Yeah.
Then coming to your, I think it's also important to clarify the calorimetric point. Okay, sorry. Uh, okay, so the calorimetric. So here, what I'm measuring is not the device level switching loss. It's the system level power loss.
Yeah,
And this is not possible to measure with the double pulse, because double pulse only tells me
that's
what
right.
is the switching energy for one event, right? It does not tell me what is the switching energy over let's say, I
Full
mean,
cycle,
it,
right?
yeah, it does not tell me what is the total power loss over the sine wave. It tells me what is the switching energy at one point on this switching,
Yeah, yeah,
right?
agreed. Yeah,
Yeah. Mhm.
that's right. The second question was like, I think I might have to discuss with you. Why do you
Yeah,
think
yeah. If it's
silicon carbide is not it's not suitable at high power and it doesn't yield any benefits, but high temperature, like I think the limiting factor is packaging, not the die. When you said die doesn't yield much benefit, like can you explain further? Like it was later in
Yes.
the slides in the last.
Yeah, yeah. Mhm. Okay, so let me go here. Okay, so okay, maybe the maybe let me let's say refine let me refine my words a bit, because I don't want this to be a source of confusion. So what I mean is that when you go to higher or when you can allow higher junction temperatures or higher operating junction temperatures, right?
Hmm.
The I mean, when you do it for both technologies, both for silicon and for silicon carbide, then the gap between silicon and silicon carbide narrows. This is what I meant. But then you have to also consider that if you look today, right, we are limited even for silicon carbide devices, right? We are mostly limited to
Yeah,
175 degrees Celsius. And this limit is not coming because of the die itself, like you correctly
yeah,
pointed out. It's coming because of the system around the die. It's coming because of the
that's
package.
right.
Because if you consider a discrete device, right, it has a certain plastic around the chip,
Hmm.
and
Yeah,
this plastic is not stable at higher temperatures. For
hmm.
example, at 200 degrees Celsius, right?
Yeah, yeah,
So the junction temperature is more for silicon carbide. This is today more restricted by the package. You
that's
are
right.
absolutely right
Yeah,
here. Uh, and even for silicon, right? Today, even though we are restricted to, let's say, 150 degrees Celsius, I still see that there is potential to go higher with silicon devices,
but
because the
silicon
limit,
by itself by nature, the device can't scale to higher temperatures, right?
yes,
Silicon carbide can go until, let's say, more than 400 or close to 800 degrees C. But
yes,
silicon, I think, has a temperature limit. You can't
yes,
scale it
yeah.
further.
Yes.
Yeah.
So the limit is coming from the leakage current, because if you take a device, right, there is intrinsic behavior of the device,
Yep.
which causes which causes a leakage current which is dependent on the temperature. Meaning that when the temperature increases, right, the device, even though you don't bias it, it starts to conduct more and more.
Hmm.
And after a certain point, it starts to behave nearly like a conductor.
Yeah.
So this is called the intrinsic behavior. And for silicon, this temperature is much lower. I don't have the number on top of my mind, but this is much lower than for silicon carbide. So from that point of view, if the package is capable of higher temperature, right? Or if the package can enable higher temperature, I think
Yeah.
silicon carbide will offer this benefit also at higher temperatures.
Yeah, I think historically, well, you can correct me if I'm wrong. You come from Infineon, you have more information. So packaging was built to withstand around 150 to 175 degrees C because silicon's theoretical limit of temperature was close to that limit, right?
Mhm.
And then
Yes.
today, suddenly silicon carbide is capable of doing way higher temperatures, but suddenly the
Yes.
packaging can't is not there. So
Yes.
that's why the limiting factor on packaging has come
Mhm.
to light today, right?
Yes.
Yeah.
Yep. Mhm.
So
Yeah.
Thank you, Karthik. We'll move on. There are lots of other questions. Please email Dr. Ajay. He'll be happy to answer any questions. Hafiz, please go ahead with your question fast. Hafiz,
Hello, Ajay.
yeah,
Thank you
please
so
go ahead.
much. It is very nice to hear you again.
Nice to hear
Um,
you again too.
I have a couple of questions.
Please.
Like we saw that almost 75% of the losses when you compared between IGBTs and SiC MOSFETs are because of the bipolar behavior of the IGBTs. So how would you compare SiC MOSFETs with standard silicon cool MOS from Infineon? Like for 400 volt system, why wouldn't you employ a 800 volt cool MOS or 900 volt cool MOS device, which is a much mature technology as compared to SiC?
Yeah. I think this is a very interesting question. So maybe I will answer it more from the super junction MOSFET point of view. Uh, I think it
Mhm.
applies to super junction MOSFET. So super junction MOSFETs, they are mostly designed for fast switching applications and not for
Yeah.
traction inverter applications, meaning that they are designed for higher switching frequencies. So for example, super junction MOSFETs can do, let's say, in the range of 150 kilohertz, but they have a disadvantage that they are not, let's say, 100% compatible with hard switching applications. And traction
Yeah.
inverter is clearly a hard switching application, and therefore super junction devices are not really compatible. So therefore,
Okay.
we cannot use super junction devices for the traction inverter application, because the body diode of the device has a restriction.
Okay. Okay. All right. The second question is about what is limiting gallium nitride devices to be used at 400 volt, except they are
Mhm,
like normally turned on devices,
mhm.
but we can put them in cascode configuration. So why would someone use a gallium nitride, and why
Mhm.
should we choose SiC MOSFET for that?
Yes, I mean, I think there are, I have seen in conferences and trade shows some prototypes of inverters which were built based on gallium nitride.
Yeah.
So I think it is theoretically possible. For me, it's just a question of reliability and maturity. I mean, if you look in one of the first slides, right, I showed that for automotive, it's very important to have a low field failure rate. And
Exactly.
GaN is a rather new technology, and there is not so much field experience for such applications. So I
But the
think at the moment,
wafer, the main wafer is standard silicon wafer for GaN. Like
yes,
so, silicon carbide is, in my humble opinion, like you are better to comment on this, but silicon carbide is a completely new technology.
yes,
GaN is like a standard silicon wafer, and on top of that is
mhm,
developed.
yes, yes. I mean, I fully agree. So with silicon, for GaN, the advantage is that you can fabricate GaN devices on a silicon wafer, right? Which means
Yes.
you don't need a, let's say, a more expensive material like silicon carbide wafer, right?
Yeah.
But then we have to also keep in mind that the actual conduction in the device, right? This is happening still in the GaN layer. So the
Yes.
silicon layer is just like, I mean, for a pizza, it's like the crust of the pizza, and the actual flavor is on top of the pizza, right? In the same
Hmm.
way, for GaN devices, the actual flavor is in the GaN layer, which is on top of which is grown on top of the silicon. So silicon is just for a mechanical base. So therefore, even though it's let's say fabricated on silicon wafers, I think it is still not clear what are the failure mechanisms of GaN, for
Okay.
example. And
False turn on. It suffers from false turn on, right?
yeah, I mean, I wouldn't claim that as I think there will be solutions to that. I don't want to comment too much on that, but I think for me, it's just a question of reliability or maturity, let me say, not reliability. I think GaN has still some, I mean, GaN has to prove itself in applications like telecom, power supplies for a certain time. After that, it might come also for automotive. I don't rule out that GaN will not be used for automotive applications, but I
Okay.
just think now is not yet the time for GaN.
Mhm.
Got
Talking
it.
about the reliability of SiC devices, like I am not an expert on that, but I read somewhere that the oxide layer in SiC is not so reliable till now, and there are like lifetime issues with that.
Mhm.
Is it now mature enough to be employed in automotive applications?
Yes, I mean, I think it's mature enough because we already see a lot of release products which you
Yeah,
will find on.
I think, sorry to interrupt, I think Model 3 has uses SiC devices, right? Model 3 inverter
Yes.
uses SiC. Yeah.
Well, I mean, I cannot comment too much on that, but let's say based on information which is available in the public domain, right? If you
Mhm.
look at Infineon website, you see already parts which are released for silicon carbide. You will find that we have released silicon carbide MOSFETs, maybe not exactly for the traction application, but for onboard charger applications. But we think that silicon carbide is capable of automotive quality fully.
Yeah, yeah.
Okay. Okay.
Okay. Thank you,
Uh,
But
Hafiz. Yeah. Go
yeah,
ahead,
but
Dr. Ajay.
agree. I agree with you that silicon carbide is still. I mean, the field experience, right? If you compare with IGBT, it does
mhm.
not have the same field experience. But I think it's just a question of time before the field experience is being gathered.
Okay.
Okay.
All right. Thank you.
Thank you,
Thank you so
Hafiz.
much.
We'll take one last question from Arshia Mirza. I hope I pronounce it properly. Please go ahead quickly.
Uh, yes, please. Thank you. Very good presentation, Ajay. I have a couple of questions here. Um, I work mostly with related to insulation materials. So I was looking at so are filters used in specific applications to electric vehicles and electric vehicle drives? So are filters used wide bandgap filters? So
Mhm.
are filters used after the inverters? And so we'd expect not a near to sinusoidal wave pulse
Mhm.
before the motors.
Mhm.
So what do you think are the effects of inverters on insulation materials and
Mhm.
specifically insulation cables and motor stator due
Yep.
to their fast rise times and slew rates?
Yep.
And do you think what could be a good scope for research in
Okay.
electric vehicles and medium voltage?
Yeah. Um, So I think there are at least three parts in your question. I will try to tackle it in three different parts. So first part is, do we use filters today in automotive applications, right? I think this is what I
Mm-hmm.
captured. So
Yes.
yes, filters are used today, but not, I mean, typically there is no filter between the traction inverter and the motor. Why is this?
Oh,
Because the motor has a large, I mean, motor is finally a lot of inductance, right? And this
yes.
filters already a lot of the high frequency transients. So therefore, the motor itself does not need any filters. I mean, today it's not common to use filters here, but there
Mm-hmm.
are some EMI filters which are used on the DC side. So on this side, if you can
Okay.
still see
Yeah.
the pointer. So it's common to use EMI filters on this side because we don't
Okay.
want the high switching transients on this side to go back to the battery and then let's say to the radio of the car or to the microcontroller of the car, which is critical. It should not. So
Okay.
the switching here should not interfere with other applications in the car, which could be critical. For example, let's say you have the electronic stability program, right? The ESP, and this is
Mm-hmm.
controlled by a microcontroller. Let's say this switching waveform here interferes with the ESP, electronic stability program, and then you could have dangerous consequences. So therefore, it's not allowed for the transients to go back to the battery side. So there are filters here. Also on this
Okay.
onboard charger system, right? If you look at the onboard charger system, this is where you would connect to the grid, to the local grid of your house or of a charging network. And we are not permitted by law to inject harmonics back to the grid. In Germany, for example, there is this BDEW Richtlinie, which suggests or which regulates, what should be
Mm-hmm.
the limit of the harmonics on the current or the on the current here on the grid side. So therefore we would need to install a filter here on this side of the onboard charger. So therefore onboard charger typically has filters both on the input and the output side. But the traction inverter has filters only on the input side. I think this is more or less answering your first question. Second was, I think it was more to do with the insulation of the machine, right? Like I mentioned
Yes.
today, yes. So the windings of the electrical motor are restricting the switching or the maximum possible DVDT which is permissible on the switches here, which means we cannot switch faster than, let's say, 15 kilovolt per microsecond, because we would end up killing the insulation of the electrical motor. So this is not allowed. So maybe one, I'm not so much into the filter design, but maybe one, let's say, area which is at least to me not very clear would be how could you, for example, insert a filter here between the motor and the traction inverter so that you could gain more efficiency of the traction inverter. So this could be one area of further research to answer your third or to answer the third part of your question. Because in the end, right, let's say we insert a filter here, and because of the filter we can switch faster on the traction inverter, there will still be some losses in the filter, right? So basically we will have lower losses in the traction inverter, but some more losses on the filter. And then in the end, I'm not sure if the trade-off is good enough. And secondly, the filter will also add some cost on the system. So
True.
in the end, whatever systems we add, right, I think it has to make this complete system cost effective. So I'm not sure if there is a cost optimization possible with such a filter. But I think this would be a good area of research. Honestly, I cannot comment if there is a lot of work going on here. But I think this
Okay.
could be a good area of research.
Sure. But thank you so much.
Okay.
Welcome.
Thank you very much, Dr. Ajay. Thank you very much. There are some more questions. Probably I'll send it to you because there are way too many questions. I will probably send it to you. Thank you for your time. Thank you very much for giving such a detailed thing. And were there any specific questions from the reviewers or from the examination committee? Did they ask for more results? What did they ask?
Yeah, there were a lot of questions. But I think most of I mean, there is normally two-part, or there are two parts to the defense procedure. So one is on the presentation itself, then is the examination on the thesis. So I think on the presentation itself, it was well received, but of course, there were a lot of questions. And honestly, I found the questions quite good. And most of them were to do with the specifics of the method, to know what are the boundary conditions of the comparisons and so on.
Good, good.
But I found them quite relevant and challenging, to be honest.
Okay. Good. Thank you very much, Ajay. Dr. Ajay, we'll let you go.
So maybe as a last point, if someone is interested, so the thesis is now available on two places here. So if someone is interested to know more, feel free, or also to contact me if you have if you need something more.
Yes. Very good. So this is okay. This is on the university website. Okay. Or
no.
this
So this is published by Shaker Verlag and also available on Amazon.
Amazon. Okay.
Yes.
Good. Spectacular work, Dr. Ajay. Thank you for your time. It's very hard to get engineers from industry to spare their time, and we appreciate your patience in explaining all the concept and answering all the question. I hope, I'm sure everybody found it very incredibly useful, and we thank you for your time and hope to see more publication from you, hopefully.
Yeah, thanks a lot. Also from my side, I think it was really nice opportunity to present directly to all of you. And also the questions, I found them really challenging and very relevant. Thanks a lot.
Thank you very much. Yeah, thank you everyone. We'll end
Okay,
this.
yeah, then good night. Thank you.
Good night.